Hello everyone. In this demonstration, we'll be briefly covering the general design flow for Lattice's embedded design software, Lattice Propel. For those that are not familiar with Propel, Propel is a software suite that is used for creating soft processor-based FPGA designs. Propel consists of two main tools, Propel Builder and Propel SDK, each of which have specific usages depending on the part of the embedded design that you're working on. Propel Builder is a graphical tool that is used to interface IP and generate the RTL that we will use for our soft processor-based designs. And Propel SDK is an Eclipse-based IDE that is used to debug and develop embedded applications for the soft processor designs that we create in Propel Builder. Today we'll be using Propel's template designs called the Hello World project in order to try out and learn more about Propel's embedded design flow. So to begin, we'll start from Propel Builder, whose main GUI interface looks like the one that you can see on my screen now. If you notice any significant differences between what I'm seeing and what you're seeing, make sure that you're using Propel Builder and not Propel SDK. Functionally, either tool can be used as a starting point for SoC projects. However, today's exercise will be beginning from Propel Builder. With that said, first off, we'll need to create our SoC project, which we can do by clicking the new design icon from Propel's toolbar. From the pop-up window that appears, I'm going to define a name for my new project, which I'll call LFCPNX_SoC. And then I'm going to select the location that I want to save my project to. Now that I've done that, I'm going to click Next to continue on with the project creation process. In this portion of the project creation window, we need to select the target device and template for the project that we want to create. For this demonstration, I'm targeting the Certus Pro NX Versa evaluation board. So I'm first going to select the LFCPNX as the family dropdown, and then LFG672 as the package. Lastly, I'm going to select 8 high performance for my target device's speed grade. Although I'm targeting a specific device for this demonstration, you should be able to follow along using any device, as this demo is not board specific. With that said, from the template section of this page, select Hello World Project in order to use that as a source template for our new design. And then click Next, and then Finish. As can be seen from my screen, the project template that we selected includes a RISC-V CPU, several bus interface modules for AHB, Lite, and APB, as well as a GPIO and a UART. Any of these components can be modified or reconfigured. However, you need to have a version of that IP installed locally first. Otherwise, you'll see an error like the one that I'm seeing on my screen now. With that said, to install an IP from Lattice's IP server, select IP Catalog from the left side of Propel Builder, and then select the IP on Server tab towards the top of this window. From the IP on Server view, scroll down until you find the UR-IP and the RISC-V MC IP with the highest version numbers, since we will be modifying both of these IPs shortly. At the time of this recording, which is near the release of Propel 2023.1, the most updated versions for each of these IP are version 1.3.0 for the UART and version 2.4.0 for the RISC-V MC. Once an IP has been installed, you can generate it and instantiate it to your current design from the IP on Local tab. You'll notice here that there are two categories of IP on IP on Local. IP under the Module section are components which come pre-installed with each version of Propel. These include foundational IP, such as oscillators, PLLs, and bus interconnects. The second section, under IP, are IP which have been installed from the IP server. To view more information about any IP, simply click the blue question mark next to its name, and the help information for that IP will appear at the bottom of the Propel Builder window. This additional help information includes the device support, version history, and the user guide link for the selected IP. With that said, to begin generating an IP, double-click it from the IP on Local tab. For this demo, we will be generating another version of the UART IP for our design, which we will call my_UART. The second page of the IP generation window is where we will set the parameters for our IP's configuration. For this demo, we'll leave everything as its default values, and then click Generate and then finish to finish generating the IP for our project. Whenever a new IP is generated for a project, Propel will automatically prompt us, asking if we want to instantiate it to our current design. Click OK so that the UART we just generated is also instantiated, and as can be seen from my screen, the UART is now added to the schematic view of our SoC design. At this point, there are a few additional things that we need to configure in order for us to be able to use our custom UART within our design. The first change that we need to make is with the FPGA interconnect. To reconfigure an existing IP, simply double-click it from the schematic view, and then from the IP configuration window, change the parameters that you want to update accordingly. In this case, we'll be changing the total APB slaves parameter from 2 to 3 so that we can connect our new UART component to this interconnect. Next, we're going to modify our RISC-V MC component, and once again change the number of interrupts from 2 to 3 to support our UART. Once again, click Generate, and as can be seen from my screen, both components were updated accordingly in order to support additional interfaces which we can use to connect to our UART. To make connections, simply left-click the source port that you want to make a connection from. If you clicked in the correct location, a wire will appear from the source port or interface that you selected, and follow your mouse along until the connection is completed. To complete the connection, simply left-click the destination port or interface that you want to make the connection to. For this demonstration, we'll be connecting the interrupt output of our UART component to the interrupt port of our RISC-V processor, as well as the APB interface from our UART to the APB interconnect that we updated earlier. With that out of the way, there are still a few additional connections that we need to make. However, I'm going to right-click and then select Auto Connect in this case in order to finish a few of these connections in just one step. Depending on the unconnected ports and interfaces in your design, Auto Connect will suggest various connections to help you complete your design. In this example, we will be connecting the clock OS port from the PLL in our design and the reset from our RISC-V to our UART component. The last connection we will deselect, as the suggested connection is not aligned with what we need to do for this demo. The last two remaining ports for our custom UART will be connected at the top level of our design. However, we need to create the top level ports to connect the component to. To create a top level port, you can either right-click anywhere in schematic view and then select Create Port, which will open the port creation window up, or you can right-click the component with unconnected ports and then select Export, which will automatically create top-level ports for all the unconnected ports of the component that we select. Both methods work for creating top-level ports. However, I prefer to export ports in some cases, as it's semi-automatic and doesn't require us to define settings like the direction, width, and type for all of the ports that we want to create. With that said, you'll probably notice that these generated port names are very long and generic. To change these generated names, first select the port whose name you want to modify, and then select Design View from the left side of the Builder window. Using the Properties section at the bottom of the page, change the name of the first port to my_rxd_i, and then click Enter to apply the new name. And then repeat the same process for the other exported port by first selecting it from schematic view, and then changing the name in Properties to my_txd_o, then clicking Enter. Lastly, before we leave Propel Builder, I want to quickly take a look at the Address Space tab, which contains the address mappings for all the components in our design. As can be seen from the bottom section of this address tab, the custom UART component we created appears as part of the memory map connected to our RISC-V's data bus. If you want to modify the address mapping for any of the components in our design, double-click the base address section. If you are content with your address mapping, click the lock icon towards the right side of the window, which will lock your selection and prevent it from being overwritten if you use Propel's auto-assign feature. For this demonstration, we'll be leaving everything as their default values, so we don't need to make any changes here. Lastly, to ensure that there are no violations with the address mappings for our project, click the Verify DRC icon from the toolbar. If there are no errors reported in Propel Builder's Tickle console, then there should be no issues with our project's address space mapping. With that in mind, we'll now click the Radiant icon from Propel Builder's toolbar, which will launch Radiant and automatically invoke a tickle script that will generate a new Radiant project and add all of the components from our Propel design to it. Once Radiant opens up, there are only a few additional things that we need to do before we can proceed onward with the project development process. The first thing that we need to do is modify the strategy settings for our project. To do this, right-click Strategy 1, which is the currently active strategy for our project, and then click Edit. From the navigation section on the left side of the pop-up window, click Place and Route Design, and then change the number of placement iterations from 10 to 1. The reason we're modifying this setting is because I already know that our design will most likely not meet timing, so I don't want the placement engine to spend too much time trying to improve timing by running multiple iterations if the difference will not be very significant. Next, click the bitstream header from the left side of the window and enable IP evaluation mode. This setting is required for this demo as we're using several IP which require licenses. Enabling this setting will allow us to generate a temporary bitstream, which is valid for 2 hours, even though we don't have the required licenses for the IP in our project. Once you finish updating these two settings, click OK to save those selections. And now that we've finished updating our strategy settings, we can continue on with the project development process by clicking the Export Files button from the Process toolbar, which will run through each stage of the Radiant process flow, automatically running through synthesis, map, placement and routing, and bitstream generation in order to generate a bitstream for our project. This process is going to take some time, so I'm going to cut away and return once the bitstream is generated. Now that the bitstream for my project is generated, all that's left for us to do in Radiant is program our target device with this bitstream. To do this, click the Programmer icon from Radiant's toolbar, which will open the Device Programmer standalone tool and automatically create a new programmer project for us. Before programming our target device, we first need to select the USB port that it's connected to. To do this, click Detect Cable and then select the corresponding USB port that our device is connected to. In my case, my device is connected to USB 0. However, you may need to select something else if you're not able to detect your device when you attempt to program in a little bit. Aside from selecting the correct port, another thing you need to try adjusting is the TCK divider setting. In some cases where you cannot detect your target device, but do have the correct USB port selected, adjusting the TCK divider to slow down the JTAG clock speed can help programmer detect your device. With that said, before programming your device, you should also double check to make sure that the correct bitstream is selected in Programmer. If you loaded Programmer using the same method that I did for this demo just now by clicking the icon from Radiant, then the most recently generated bitstream for your project will automatically be selected here. However, if you notice that the incorrect bitstream is selected, or that no bitstream is selected, you'll need to double-click the file name field, and then locate the correct bitstream programming file that you just generated. With that said, click the Program Device icon in order to program your target device. Once programming finishes, you'll see a new message output to the Programmer console, indicating that the attempt to program was successful. Now that we've finished programming the target device for our project, the final step is for us to return to Propel in order to generate the C application for our SoC design. So there are a few different ways that Propel SDK can be launched, but one of the most convenient ways is to launch it directly from your project in Propel Builder. To do this, simply click the Propel SDK icon from the toolbar, and your Builder project will automatically be exported to Propel SDK. After a few seconds, a workspace selection pop-up will appear. A project workspace is essentially the directory where your C project's files will be generated and saved. The location that you select at this point can vary from project to project. However, for this demonstration, I'm going to create a workspace directory within my SoC Designs project directory to make file management a little easier. As mentioned before, however, this step is optional, and you can select whichever workspace you like, as this can also be changed later on. With that said, click Launch once you've selected a workspace in order to launch Propel SDK. One of the benefits of launching Propel SDK directly from Propel Builder with the project open is that the new C project window will open automatically with the relevant files from your SoC design selected by default. As can be seen from my screen, the system environment XML file, which describes the hardware architecture for our SoC project, was automatically added and selected here. If you do not have a system environment XML file specified here, you can select it from the SGE directory of your SoC Designs project directory. With that said, I'm going to create a C project, which I'll call lfcpnx_sw, and then click Next to continue on with the project creation process. In this page, I'm going to select semi-hosting from my systems library, which will enable us to emulate direct communication with the UART in our design without having to do any board level setup. This option is very convenient and also frees up the JTAG connection on our device while debugging. With that said, click Finish, and as can be seen from my screen, a new C project called lfcpnx_software was created and added to my active workspace. Before we proceed, I want to quickly point out a few things about the hierarchy for these generated C projects. The first of which being the actual contents of the BSP folder, which contains the drivers for all of the IP in our design, which come with drivers. As can be seen from my screen, the IP that come with drivers in this specific project are the GPIO, UART, and RISC-V processor. Aside from drivers, there's also a sys_platform.h file, which is a header definition file that contains parameter level definitions for all the components in our design. This file is useful as it contains parameter definitions for the various address ranges of the addressable components in our design, as well as other parameters which are dumped from all of the IP in our project, which can be used to improve portability and scalability in your own code. The last file that I want to point out here is main.c. As its name implies, main.c is the main file for our project, which contains some generic code depending on the components in your design. As can be seen from my screen, the code initializes some of the components in our design, like the GPIO, UART, and programmable interrupt counter, and then prints out hello world while also toggling the GPIO output. For the purpose of this demonstration, we're going to copy the hello RISC-V world printf statement and add another one inside the main portion of the while block in our code at line 83 so that we can see the print statement cycle continuously while we debug. Lastly, before we begin debugging, I'm also going to add two breakpoints at the beginning of main and also at the second printf statement of our code. To do this, you simply need to right-click the leftmost column and select Toggle Breakpoint at lines 83 and 52. Before we begin debugging our design, we first need to build it once in order to generate the executable file that is used by Propel's debugger. To do this, simply right-click the name of the project from the project file list on the left side of the window, and then select Build Project. Doing this will generate an additional debug folder in our project, which contains important files such as the .elf, which is used for debugging, and .mem file, which is used to initialize the project's system memory separately from Propel SDK's debugger. With that said, now that we've finished setting up our C project, the final step is for us to create our debug session and then begin debugging. To do this, select Run and then Debug Configurations from Propel's toolbar. From the pop-up window that appears, double-click GDB Open OCD Debugging in order to automatically generate a new debug project for the current project. Doing this will automatically populate several settings, such as the project name and C application file, that we would otherwise need to input manually. Next, select the CableCon tab, and then click Detect Cable in order to detect the cables that are currently connected to your PC. Once we've done that, use the drop-down to select the same port that we used to program our target device, and then click the Scan Device button for Propel to detect the actual connected device. If all goes well, you should see the name of your target device in this window. However, if there are some issues, you should ensure that your JTAG connection is not actively being used for something else, like programming or debugging with Reveal. Otherwise, you may see no device here, or a plus icon instead. If the issue persists, try changing the TCK clock divider setting to slow down your JTAG clock frequency, or power cycle your device and attempt to reprogram it. With that said, Once you've scanned for your target device, the final step is to click Debug in order to begin debugging. One thing I quickly want to mention before we proceed is that the default color for text when debugging in Propel is red, so don't worry, as this does not necessarily indicate an error has occurred. As OpenOCD loads, a pop-up will appear asking you if it's okay to switch to the debug perspective. Click the switch button and continue to wait as OpenOCD loads. And now that OpenOCD has finished loading, we can see that our debug session has stopped at the first breakpoint for our project, and that we can use the resume, step over, step return, or step into icons from Propel's toolbar in order to step through our code. For this demonstration, I'm going to click the resume button, and as we can see from the console output, our semi-hosting is working as expected, with Hello RISC-V World being printed out each time I click resume to jump between breakpoints. Before we conclude this training, I want to quickly point out a few additional views which may be useful for your own future debugging. Some of these views include the variables window, which will display the variables in the active file that were updated each time you step between breakpoints. Aside from that, there's also the breakpoints tab, which can be used to manage the breakpoints in your project, and can be used to enable, disable, or add additional breakpoints depending on what you want to do. Aside from that, there's also the peripherals tab, which can be used to enable or disable the register views for the various memory mapped components in your design. To use this debugging view, simply enable the peripheral whose address space you want to view using the checkbox next to each respective peripheral's name. And as can be seen from my screen, the peripheral's instance and corresponding registers will be displayed in the memory section at the bottom of the window. That concludes this demonstration walkthrough. Thank you all for your time and attention.